Yeah.
Exactly, because I actually take my classes on WebEx. So I was very,
Yeah, right.
I told Shashi, no problem, others say WebEx, what is it? But I'm used to it. So we also have IIT Madras, the WebEx connection.
Professor, now IIT Madras, it is online classes is going on or offline?
Yeah, still online.
Still online. So is there any idea when these offline classes will start? No.
Probably in a month or something. We are hoping. It's still.
Okay.
We were thinking of hybrid, but it is not yet.
Okay.
Because only 50% of our students are on campus.
Okay. Yeah. Yeah.
By the way, this share thing can.
Yeah, sir.
Yeah.
Please.
Still, I think it's muted. I mean, I can't share.
Sorry?
I can't seem to share the share button.
As a co-host also, I think it should be there, right? Yeah. I think now it should be there.
So, yes, absolutely.
So is it now visible?
Yeah. Are you able to see?
Not yet.
Okay, it says it's loading. Seems to be taking a long time to load.
Yeah, now we can see.
Oh, is it? Good. I think these keynote files are large. Yeah. Shashi, you can see?
Yeah, I can see, sir.
Okay, very good. So I think we can start. Only thing I can't see anybody except my presentation. So if there is anything, please let me know.
Sir, somehow your sound is still quite low.
Is that now any better? I'll just try to speak more louder.
Yeah, that should be better, yes.
Okay, let's try, because I don't want to risk putting a speakerphone. Okay.
Yes. So I can hear Professor Lakshminarayan properly. So can you hear Shashi from your place?
Yes. Now we can.
I can hear him properly. No problem.
Yeah. Okay. Good. Yeah.
Okay. Great. Should we start?
So, so shall we start now?
Yes, please.
Yes, sir. Yeah.
Okay. So, dear colleagues, ladies and gentlemen, as part of the year-long celebration of Azadi Ka Amrit Mahotsav and on the occasion of National Science Day today, we are honored to have among us a distinguished speaker, Professor Lakshminarayan, Arul Lakshminarayan from the Department of Physics, Indian Institute of Technology, Madras. He has kindly consented to deliver a special VECC colloquium titled 36 Entangled Observe of Euler, Quantum Solution to a Classically Impossible Problem. A very warm welcome to you, Professor Lakshminarayan. In the spirit of Azadi Ka Amrit Mahotsav, where we celebrate India's achievement in the last 75 years, I feel the topic of today's colloquium is very appropriate, where a quantum solution has probably been provided to a problem which is almost 3 centuries old. Let's listen to Professor Lakshminarayan more about this scientific field. So I think now, Shashi, please, can you please introduce Professor Lakshminarayan?
Yes, sir. Thank you. Thanks, sir, for your opening words. Now it's a pleasure to introduce Professor Lakshminarayan. And Professor Lakshminarayan is by training a mechanical engineer from IIT Madras, but then he switched to do his PhD from State University of New York at Stony Brook in theoretical physics back in 1993. Subsequently, he joined Physical Research Lab at Ahmedabad before he moved to IIT Madras in 2003. He has been a regular visitor of Washington State University Pullman, IIT Kanpur, Max Planck Institute in Dresden, and several other places, namely Krakow, Poland, where this current work was carried out partially. So Professor Lakshminarayan got entangled with chaos quite early in his career. Some of his early works conclusively showed that chaos was instrumental in entangling subsystems efficiently and nearly maximally. So on one hand, he has worked in purely mathematical concepts in random matrix theory, be it the average properties or the extremes. On the other hand, his results find a place in many body literature, again, whether it's a thermalization or lack of it, or it is out of time ordered correlators. So apart from being outstanding in his research, he's a great teacher and loves to work with students all the time. A number of undergraduates doing their project, which resulted in research publication, is testimony to that. And some of the glimpses you will see while you hear Professor Lakshminarayan during this talk. His PhD and postdoc students are now placed in various institutions of India. And that's just a few of the things which I thought I'll bring out in front of you. But I mean, this is nothing compared to what he is going to talk about today, namely this 36 entangled officer of Euler quantum solution to a classically impossible problem. So dais is yours, sir.
Thank you very much. It's a great pleasure and honor to be here at the Azadi Ka Amrit Mahotsav at VECC Kolkata. Thank you very much, Professor Shom and others, for this very kind invitation. And I have had the pleasure of visiting you. In fact, I've had long collaboration and association with Dr. Shashi Srivastava, who said all these kind words about me. And in fact, a lot of my work has been with Shashi himself. And so it was a pleasure when he asked me to if I can talk about this work of ours at your special colloquium. So it is indeed a great honor. Thank you very much for the invitation. So this work is, as you can see, titled 36 Entangled Offices of Euler, Quantum Solution to a Classically Possible Problem. It has been done in collaboration with my PhD student, Suhail Ahmad Rada, and these other postdocs and PhD students of Professor Karol Szyszkowski, Adam Burkhardt, Wojtek Bruszta, Grzegorz Rachel. All of them are at the Jagiellonian University, Krakow, which, for those of you who don't know, is one of those ancient European universities. It counts among its alumni Copernicus, so it's really one of those old universities which has seen the transformation from a world of science dominated by Christianity to that of modern science. And Suhail and myself, we are at the Department of Physics, the Indian Institute of Technology, Madras. So what I'm going to talk about today is, has just appeared recently in Physical Review Letters and has been highlighted in this article by Philip Ball. So I think very nice expositions are already written on this work. So it's kind of peculiar that the author is going to talk about it now. So in this particular feature article in the APS website reads a quantum solution to an 18th century puzzle. So what I'll talk about today is more at a colloquium level. I'm going to keep the mathematical details to absolutely minimum, but at the same time, I want to say that actually a lot of things are in the imagination and we can imagine things, and we are actually used to solving these kind of puzzles probably just every day in the morning, for instance. Sudoku. Sudoku is something which we are all very familiar with. And look at this solved Sudoku. Okay, so I'm not going to try to solve it. But you can see that we all know what this is. So,
excuse me, sir.
Yeah.
I think slides are not changing.
Oh, is it? Okay, that's not good. You're seeing the 36. Okay. This is a problem. Shashi, now it's changing, right?
And still we can see the title slide.
Only this?
Yeah.
Oh. Yes, you're right. Nothing is changing?
No.
No. Okay.
Maybe unshare and share.
Okay. Unshare and share. Okay. See, it doesn't allow me to share the whole screen. It only allows me to share the Okay, let me try to do one thing. Let me try to share PDF file rather than this thing. Let's see whether. It's loading too many files.
Professor, you may use a PDF file if you have. That will be, I think, better.
Yeah. So let me log out from here. Okay. Could you please, I can't, now I have logged in from another machine, but I'm not able to, can you make me presenter on this?
Yeah, just Sir?
He's unable to. He's trying.
No, now it should be fine. You're able to see my screen, right?
Yes.
Okay, now we are free from the things of Keynote. Now you can see the second slide.
Yes.
Okay, thank you. And again, apologies. So that's Shashi. How much time should I aim for? It's 4:20.
I guess 45 minutes.
Okay. So again, I apologize for this hitch from Chennai to Kolkata. And so let's come back to this. Okay, so we are quite familiar with this puzzle of the sudoku. What is it? So there are these numbers 1 to 9, which is arranged so that nothing repeats along any row or column, right? Along any row or column, there should be no repetition. And also, Sudoku has an additional constraint that within these 3 by 3 squares, there be no repetition. And there are 9 such squares. Now, we are going to first look at much more simpler objects than the Sudoku. Okay, but even that holds very interesting things for us. These are called Latin squares. Okay, so let's look at this Latin square 1. It's just a 3 by 3 array, unlike the 9 by 9 array of the Sudoku. It has these three numbers 1, 2, 3 arranged such that along any row or column, there is no repetition. Okay, so that's clear. 1, 2, 3, 2, 3, 1, 3, 1, 2, and so on. So this is a kind of a magic square, which has a long history, I believe, in Indian mathematics as well. And if you look at the second square here, that's another example of a Latin square. It's different. Okay, the entries are different, but it has the same property. Now, what happens if we put these two Latin squares together? So I'm just taking this first Latin square and making a union of that with the second Latin square. And what you see is that these entries are now 1, 1, 2, 2, 3, 3, 2, 3, 3, 1, 1, 2, and so on. Okay, so this now has two entries per cell, and the two entries are such that none of the first entries are the same. Okay, so each of the first entries are different. So also the second entries are different. Okay, so as you go by, you can see that there is no repetition along the first or the second indices. And not only that, this is most important, all possible combinations, all the 9 possible combinations from 1, 1 to 3, 3 appear here. Okay, so there are these 3. So you're putting together a set of 3 objects, 2 sets of 3 objects. You have 9 possible combinations. All 9 of them appear here. And there are only 9 cells, so they can obviously appear only once and uniquely. So if that is the case, then this is called an orthogonal Latin square. Okay. So that's a definition of an orthogonal Latin square, which I will refer to in this talk as OLS. I hope this is clear. Now, what are OLS? So OLS are, as I said, they are permutations of D square symbols in general, where D is the size of this array. In our case, in this example, which I've chosen to start with, it's just 3. So what kind of a permutation is it? So let's first just write down in this 3 by 3 array a natural ordering, where this 1, 1 refers to the fact that this is in the first row and first column. This is the second row, third column, etc. Okay, so this is lexicographic ordering, if you wish. So this is that, and this is the orthogonal Latin square, which I had in my previous slide. So now what we want to do is to say that the cell 1, 1 has the entry 1, 1. The cell 1, 2 has the entry 2, 2, etc. So now you see this is now put into this 3 by 3 array, where the address of this entry is coming in the blue numbers here, pair of numbers. So it's quite simple like that. Okay, so 1, 1, 1, 1. Why am I doing this? Why I'm doing this is because we want to ask questions like, how do you construct these kind of orthogonal Latin squares? And how many are there? And so on and so forth. Now, these appear to be rather difficult problems at the outset of combinatorics, which always is a difficult subject for us. However, we want to translate this problem into one where the mathematics is simpler and clearer. And that's why we are doing this. So because we can specify this orthogonal Latin square by a permutation matrix, which says, look, the entry 1, 1 is going to 1, 1. Entry 2, 2 is going to 3, 1. So that is how we are going to look. Once we say that, because it's just a permutation of 9 symbols here. And therefore, you end up with a 9 by 9 matrix like this, which is a permutation matrix. So this permutation matrix 9 by 9, and remember what a permutation matrix is. Permutation matrix, every row and column has only 1, 1. Everything else is 0. And every row and column has exactly one in it. So it's a permutation. Like this is how I will construct this permutation matrix, 9 by 9 out of this. I'll say that the 1 1 cell has the entry 1 1. Therefore, I'm going to put in 1 1 1 1 entry. I'm going to put 1. And there are these 9 of these combinations, possible combinations, which are there in this row, 9 of these in the column. So I hope this is clear. For example, let's take some random thing here. 3 2 1 3. So that says that I go 3 2 row, 1 3 column, I'll put a 1. And there are only 9 entries, and that is all uniquely done. And this is because it is a permutation. All possible symbols, nine pairs are there. You get a permutation matrix. How many such permutation matrices are there? There are 9 factorial of them, which is some 3,62,880 matrices. That's a huge number, even for this very simple case of 3 by 3 orthogonal Latin square. But the question is the following. If suppose we are given a permutation matrix, does that correspond to an orthogonal Latin square? Given an orthogonal Latin square, we can go to a permutation, but given a permutation matrix, which we can easily write down, any one of these 3 lakh ones, can we find an orthogonal Latin square? Because you see, to construct an orthogonal Latin square is much more harder than constructing permutations. So now let's look at a case where, well, there is a permutation. This is a very simple permutation where you're saying that to 1 1 you have 1 1, 1 2, 1 2, identity mapping. So you have no change, which is also a permutation. So, but that's just the identity permutation. Clearly, is it now? Let's look whether it is actually an orthogonal Latin square. Well, there is all the possible 9 symbols are definitely there. Look at the red part of it here because the blue is the address. If you look at the red part of it, the first column, let's say, the first entry changes 1, 2, 3, but the second entry is the same. And therefore, this is not an orthogonal Latin square. And similarly, if I go along the row, the first entry is the same, the second entries differ, and same with all the rows. And therefore, this is not an orthogonal Latin square, clearly. The permutation, which is the orthogonal, the combinatorial design, as these are called, is not an orthogonal Latin square if you start with the identity permutation. Let's take another permutation. Okay, it's even more simpler. Let's take the address. I mean, it's as simple as the identity actually. Let's take 1 1. That's the address 1 1 1 2, etc. And then we will just interchange these two. So that is 1 1 becomes 1 1 because no interchange is both of them are the same. 1 2 on the other hand becomes 2 1. 1 3 3 1 and so on. So this is called the swap matrix because I mean, it's a swap permutation, if you wish, because it swaps the addresses. So you take the address, you swap it. So now how does this permutation matrix look? It looks exactly like this. So 1 1 goes to 1, but 1 2 2 1 is the non-vanishing entry 1. 1 3 3 1 is the non-vanishing entry. So now this is a swap matrix. In fact, it is a swap operator in quantum computing for the case of 2 qubits or 3-level systems. Okay, so this is also a permutation matrix. But now is this design corresponding to this an orthogonal Latin square? Let's again look at it. Let's look at the red part of it. If you look at the first row, yes, it's different 1 2 3. But you look at the second entry, it's 1 everywhere. Therefore, it's not an orthogonal Latin square, although it is a permutation. So neither is this identity matrix, nor is the swap permutation. Both are permutations, but they don't lead to orthogonal Latin squares. So here is an example which was already I had stated. An orthogonal Latin square, it leads to an orthogonal Latin square. So we can ask what is special about this orthogonal Latin squares permutation matrix. Okay, so to help us, I have written all three of them side by side. So this is what I called first, which is leading to an orthogonal Latin square. This is the identity simple along the this thing, its identity swap also, which I have now discussed. Okay, now it's looking like our Sudoku puzzle, but it's much simpler. You see, there's only ones and zeros. So I have now, for convenience, blocked it into 3 by 3 small blocks with these colors. And just very now, can we see what is it that makes P9 special, corresponding to I9 and S9? We know that neither of these leads to an OLS. Well, if we look at it long enough, some things are clear. Some things are in fact obvious. So if we look at I9 and P9, you can see that each of the 3 by 3 blocks in P9 has only 1, 1. Each of them has exactly 1, 1. Okay? Whereas if you look at I9, the blocks, it's not like that. The first block here has 3 1s. Then there is no 1s in many of these blocks. Only 3 blocks have 3 1s each. So that is definitely something which is different from this. But let's look at swap, the permutation matrix corresponding to swap. Again, if you look at it, it has the same property. Each of the 3 by 3 blocks, the 9 of them, has exactly 1 1 in it. So that's not a defining property of the permutation matrix leading to an orthogonal Latin square, but it is an important clue. So let us look at what is the clue. So it says the following. Let's now look at the permutation which is leading to the orthogonal Latin square. If I look at an orthogonal Latin square, the first row does not have any repeating entries in the first element. First element should not repeat. Now, here is an observation. So when we look at it like this, I'm arranging it like this. What is this address? So this is the address. So 1, 1, 1, 2, 1, 3. All of this refers to the first row of the OLS. So this is referring to the first row of the OLS. And if you look at this one here, this is telling you the entry into that it's telling you the see the first entry here is the same for all of this. The and this is actually telling you what is the number which is being entered into the orthogonal Latin square. Okay, so they have to be different, and that is the important thing. The element here, the first element here refers to the block in which it's coming. So the first elements of both of these refer to the blocks. So if I look at the first row, it's clear that I cannot have more than one repeating here, because suppose 1 2 is again 1 2, then it means that I'm repeating 1 along the first row. So the first element must be different, and you see that the first element is different in these 3 blocks, and therefore along this the 1 should be distributed away from. There should be only 1 1 in each of these things. Okay, so very similar arguments can be made for along a column or along all rows, and therefore this is a necessary condition for the thing to be an orthogonal, leading to an orthogonal Latin square. But that's not sufficient. We saw already that the swap was also like that. Now we look at the difference. Okay, let's look at a difference here. Let's look at this first block. It has 1, no problem. This also has 1 here. But there is a difference. The difference is the following. If we go along this particular block, row block, the 1 occurs in this first column. Here it occurs in the second column. and here it occurs in the third column of the block. Whereas if you look at the swap, this occurs in the first column, this occurs in the first column, this occurs in the first column. So you can see that that column is not different. And in fact, that is the clue for this. So not only as you go by in the block, there should be only one, they should be in different columns. They will automatically be in different rows because it's a permutation, but they should be in different columns. And similarly, if you go along this, they should be in different rows. They will be along different columns automatically. And therefore, you can see that, for example, here it's in the first row, this is in the third row, this is in the second row. Whereas if you look at the swap, first row, first row, first row. So these are the differences between these two things. And it requires a little bit of thinking about and mulling on this. So let me just tell you the answer as to what actually makes this permutation a permutation that leads to an OLS. But it's exactly connected to this. The observation is that if Ij is this matrix element, this row here, and KL is this column index here, then this Ik refers to the block. For example, 1, 1 is this first block. 1, 2 is this block here. 1, 3 is this block. So this is a block address. And these two gives you intra-block address within the block. 2, 2 here, 3, 3 here, and so on. Okay. So, so what is the property that is required of this? There are two properties. So one of the properties is that if we look at each of the blocks, the entry should be in a different row and a different column. So, and how does one do that? One takes the first block here, and so you can rearrange this matrix so that you're looking at the block addresses rather than looking at these entry addresses. So by this 1, 1 here, I mean this 1, 1 block. Okay, and along this block, these entries here refer to the intra-block addresses. So 1, 0, 0, 0, 0, all the zeros are unpacked from the single block. Okay, so this is simply in mathematical terms, what it means is you're taking this 3 by 3 matrix and you're making it into a row vector. That's what you do. And similarly, you take the second block 3 by 3 matrix, lay it along a row like this, and you get this, lay it along a row along this. Quite remarkably, nothing is changed here. But if you do this along this, you take this and then you put it along a row, you see that this 1 comes here. Okay, so this is an operation called realignment. It's called a realignment. It's a particular rearrangement of this permutation matrix. And for the condition that this be an orthogonal Latin square, this leads to an orthogonal Latin square, this particular permutation should, this particular rearrangement or realignment should also be a permutation matrix. Okay. So it's very simple in terms of matrix elements. So let's actually look at this P9, that is what I've called this permutation matrix. IJKL gives you the address and the entry of the address. Now it tells you that this P9R is the block. So this I and K. So what we are doing is interchanging simply this J and K. Okay, J and K. This should also be a permutation matrix. So this is the this is one of the conditions. What is the, suppose we do this for the identity. Let's see what happens. We take this, unpack it along the row. Then you see that there is along a single row, there are 3 1s. So it's clearly not a permutation matrix. It's a rank deficient matrix, and this is not a permutation matrix, and therefore this cannot lead to an OLS. So this ensures, and this is actually now for the swap, if you unpack it, you will find quite remarkably that it remains exactly the same. So it's invariant, and therefore this particular a condition is a necessary but not sufficient condition. So this is also a permutation. So in fact, to summarize, this blockwise rearrangement, if it remains a permutation, ensures that the first entries on distinct rows are actually distinct on rows, on all rows, and the second entries are distinct on columns. Okay, we are still not finished because we have the other half. The second entry is on rows and first entry on column. But that just involves a transpose on one of these things. So you can think about this as a transpose and then an interchange and then a block thing. So this is called blockwise transpose. So it's an even more simpler operation than what I did. The blockwise transpose says that you take each of these blocks and then you do a transpose within each of these blocks. Okay, so you see that these are already symmetric things, so nothing happens. But this one is not symmetric, so this one comes here, and this one comes here, and so on. So this is called partial transpose, and that in terms of these indices, here the second and the fourth indices, this L and J, are interchanged. Okay, so this requires that P9 gamma, or the partial transpose, is also a permutation. So this is a blockwise transpose. So what we have done, we have taken a permutation matrix and we have done two operations on it. We have blocked it, and each of the blocks we have made into rows. So that is rearrangement. That's number one. Number two, each of the blocks we have done a transpose within. If it remains a permutation under both of these, then it is actually leads to an OLS. So let us now check. I mean, this one is a permutation. For the identity, if we look at blockwise transpose, nothing, it's already symmetric matrices here, so it doesn't change at all. And therefore, this condition holds for the identity. The partial transpose is the same. And if you look at actually the one which is corresponding to the identity, you can see that the second entry along the rows are different. The first entry along the columns are different. And therefore, that's why that condition is being satisfied. Whereas if you look at swap, the second entry is being repeated, and therefore it should not hold. So let's take a partial transpose of the swap operator. Then you can see that this block puts this one here, and in fact it's identical to the realignment of the identity operator, and it's not a permutation. Therefore, both the swap and the identity don't lead to orthogonal Latin squares. And therefore, I can state this condition now that a d-square dimensional permutation corresponds to an orthogonal Latin square of dimension d if and only if its realignment and partial transpose are also permutations. Now, this may seem like a complicated thing, but actually it is not. It's quite simple. Let me try to explain it in this in 1 minute in this way. In fact, let's take an example of an orthogonal Latin square. It's also referred to as Greco-Latin squares because in some versions, in the European versions, they entered the Latin alphabet first and Greek alphabets next. So here we have a 5x5 case where A to E is there and alpha to gamma is there in the Greeks. So you have all 25 possible combinations. They should occur exactly once, such that along any row, you have one of A, B, C, D, E, exactly one, and one of alpha, delta, beta, epsilon, gamma. Okay, along any row or column, this should be valid. And this is actually an orthogonal example of an orthogonal Latin square. This is the key observation. Given any row and column, there is entry 1 and entry 2. For example, third row, second column, there is D alpha. Entry is D, alpha is. That is the usual IJ to KL permutation. Let us look at the following. Suppose I'm given the row and an first entry. What does that fix? Suppose I'm given the second row and D. That actually fixes everything because there is only one D along this row. there is only one entry in which there is a D. And therefore, it is actually fixing the entry. So it fixes both the column and the second entry. And similarly, if you give me row and entry 2, let's say row 3 and entry is delta, it fixes immediately this E delta. So it fixes everything. So this is the most crucial lesson, that we have these 4 address and entries, but actually they are completely interchangeable in pairs. If you give me any 2, the other 2 is uniquely fixed. So this is a bijection. And it's each of them is, because it's a bijection, leads to a permutation. And that is precisely what is this realignment and partial transpose. For those of you who are familiar with quantum information theory, and those of you who are not as well, it's very curious that although I have introduced these partial transpose and realignment using these orthogonal Latin squares and sudoku-like designs, they have played a very crucial role in quantum information so far in what is called entanglement detection. And there is a partial transpose criterion of Perez found in 1996. There's a realignment criterion found. So it's a very curious thing that these 2 operations play a very important role in this context. In fact, they are related. We'll shortly be coming to entanglement. So what about orthogonal? I've been talking mostly about 3. What about orthogonal Latin squares in an arbitrary dimension D? It's very easy to see that there is no orthogonal Latin square in the most simplest case of 2, because you have only 2 symbols, and these 2 are, this is a Latin square. The only other possible thing is this Latin square. And you put them together, you see that you have 1, 2 repeating twice. Because if there is 1, 2 here, the next one here should be different in both of these. And therefore, there is, and it has to be the same here. So there has to be a repetition. So there is no orthogonal Latin squares in 2 dimension. Okay, 2 by 2, very simple. What about 3 by 3? We just saw several examples, and here is a nice way of, without writing these numbers in a colorful way to say this. There will be king, queen, and a rook here, and colors. There are 3 colors here. So along each row, there has to be 1 type of piece and 1 type of color. Okay, along each row and each column. So there has to be a king, and there has to be a different, there has to be a color different along each of these. So this is possible for the case of 3, as we saw. It's possible for the case of 4. It's possible for the case of 5. Things start getting more complicated. It's possible for the case of 7. You have to invent a new piece. Okay, there's one kind of a rook here. There's not enough pieces on the chessboard, unique pieces on the chessboard. And so this one is possible. You can see that the number 6 is missing. And in fact, this is the origin of the problem of Euler, stated by Euler, although I believe it was known in the to the public much earlier. So he stated the following: a very curious question, which has exercised for some time the ingenuity of many people, has involved me in the following studies, which seem to open a new field of analysis, in particular the study of combinations. The question revolves around arranging 36 officers to be drawn from 6 different regiments so that they are ranged in a square, so that in each line, both horizontal and vertical, there are 6 officers of different ranks and different regiments. So he's doing exactly the same thing that we are doing here. He's saying that along this thing, there be one officer from a given regiment and one from a given rank. The story goes that a king or some high dignitary was coming to inspect a regiment, and they wanted that if he samples any row or column, he's sampling all possible regiments and all possible ranks. So it's kind of a democratic thing. So that is the sampling thing. By the way, this all looks completely useless at some level. Even at the classical level, this was taken up in the 1930s by statisticians, and in what is called design of experiments. So it's a very interesting way in which, in fact, ISI Kolkata, near where you are, they pioneered these studies, in seeing how to test, let's say you're given some 6 fertilizers and 6 crops. How do you partition a land so that you are doing this in the most ideal possible way? So there are these kind of things which I don't have the time to go into. Um, so what did Euler know? Euler knew that these orthogonal Latin squares exist for all dimensions D. It's quite easy to prove that, and for Euler it was child's play. Like what we saw for 3, he could show that it's there for 5, 7, etc. For multiples of 4, it's slightly more difficult, but again, nothing very challenging for Euler. He showed that it exists for all multiples of 4. So that left only numbers like 2, which was clearly not, doesn't exist. 6, which he tried very hard, and he said, he conjectured that it doesn't exist. And therefore, he made a bold conjecture, which is unlike maybe, I don't know, mathematicians, that in fact, all numbers of the form 2 plus 4n, where n is a natural number, or n is 0, 1, 2, etc., OLS does not exist. So this got further evidence by Gaston Terry in 1900 when he proved extensively that in fact D equals 6 OLS does not exist. You can see that it's actually a very difficult problem because it involves a lot of combinations, and it's quite remarkable that without any computers, Gaston Terry proved this in 1900. And since 1900, since this came here, it enthused mathematicians to try to prove the Euler conjecture. And several people said that they proved it, but they all eventually turned out to be wrong, till something major happened in 1959, which is actually connected to Kolkata and the Indian Statistical Institute. And these are called Euler spoilers. So the famous R.C. Bose statistician, Raj Chandra Bose, along with his PhD student Shrikande, showed that orthogonal Latin squares exist for D is 22. 22 is one of these Euler numbers, 2 plus. So they showed that actually it exists, and therefore it violates the Euler conjecture. And there's a very nice article on Shrikande in The Wire in 2017. So he passed away shortly after this interview. So they showed that it exists, and this led to a great interest. And along with E.T. Parker, Bose and Shrikande showed that in fact orthogonal Latin squares exist in all dimensions except 2 and 6. So this came as a complete shock, and it made major news in 1959, 1960. Now, Shashi, would I have 10 minutes?
Yes, I think so.
So now I come to the quantum aspects of this thing here. So so let me just summarize. There exist no permutations of 4 objects such that the realignment of this permutation matrix and the partial transpose are also permutations. Doesn't exist. That's trivial to show. But this is much more non-trivial, but also known. There exists no permutations of 36 objects or a permutation matrix which is 36 by 36 dimensions, such that its realignment and partial transpose are also permutations. But now we can ask, are there quantum versions of these orthogonal Latin squares, and do they exist in dimensions 2 and 6? In fact, there are quantum versions, but it has been shown that they still do not exist for D is 2. And what we showed recently is that in fact they exist for D is 6, and hence the 36 officers of Euler do have a quantum orthogonal Latin square arrangement. In fact, the quantum versions vastly generalize these combinatorial objects, and they include these classical ones. So just a very brief crash course on quantum mechanics. Just to remind you, here is the Stern-Gerlach experiment performed really exactly 100 years ago, which showed that there exists these kind of systems which only 2 states or spin half, let's call it up and down or 0 and 1. And the state of this is a linear combination of these states. So the superposition is there. And if you measure the spin along the z direction, let's say this is up and down in the z direction, then the probability of finding it up is modulus beta alpha square, and the other probability is modulus beta square. So this is 1 and 0, 1 quantum mechanics. And this probabilities come from Born rule that probability of finding phi if the state is psi is given by this overlap modulus square. This itself tells you something which has been stated in a more elaborate way in quantum information, that only orthogonal quantum states can be perfectly distinguished. Why I'm coming to this statement is that we say that along any row or column, things should not repeat. They should be distinguished. So what is the role that is being taken by this object should not repeat? One should not repeat along a row is that states should be orthogonal along a row. That's what is being replaced in a quantum context. Now, in quantum mechanics, all the states, as you know, are represented by vectors in some d-dimensional space. And if you take two particle states, they are in a tensor product. And this leads to a very rich structure of two particle states, because there are entangled states. You have states which are not just 0 and 1 or 0, 0 or 1, 1 or 0, 1. There are these states like 0, 0 plus 1, 1, these kind of EPR or Bell states. And these are all examples of entangled states. So let's take two Hilbert spaces of dimension D or vector spaces of dimension D. Then a two particle state is given by this superposition in general. Okay. And what is and how do you say how much entanglement is there in the state? So a state is called entangled if it cannot be written as a product state of a pure state in subsystem 1 and a pure state in subsystem 2. So the solution answer to this is very simple. It says you calculate the reduced density matrix, which is the state of subsystem 1. You do this by tracing out the second subsystem. And there is a nice formula for this. It's just the reduced density matrix is 1 over D. D is the dimension I've put here. AA adjoint, where A is this, capital A is this matrix of these coefficients, which are in general complex numbers. Now, what is the entanglement in this pure state? It's given by the entropy of this state. And maximum entanglement corresponds to a case when this reduced density matrix or the state of the first particle is maximally mixed. There is absolutely no information if you access only the one particle. So it's maximally mixed. But now if you ask what is the condition for that, you can see from this AA adjoint that in fact A has to be unitary. If A is unitary, then this reduced density matrix is maximally mixed and the entanglement is maximum. So here is an example for two qubits or two level systems. A qubit is just a two-level system like the spin half particle. Here is a 0, 0 plus 1, 1, which in this thing will just correspond to A being identity matrix. And this is a maximally entangled state. And these states, as you know, are very used now extensively in quantum information and computing. For example, this entanglement can be converted to resources in quantum information, things such as here teleportation, where an unknown qubit state is being teleported to a very distant receiver by just a transmission of 2 bits of information. So this is a famous quantum teleportation protocol. I'm not going to go into the uses of quantum entangled states, but there are many, many examples of the thing. Instead, I'm going to now ask, okay, now that's just 2 particles. What if I have more particles? And in fact, this is a crucial question for many body physics. For example, highly correlated condensed matter systems are in fact in states of highly entangled states. So let's define absolutely maximally entangled states, which are actually easy to do, of n particles, each of local dimension d. It says that I can look at any bipartition of this particles. So I take some s of them and I find the reduced density matrix. It should be most mixed. Then that implies, because it's a bipartition, so if it's most mixed, that means that the entanglement of that S with its complement is maximal. So if you take any cut, it should have any bipartite cut, it should have maximal entanglement. Then such states are called absolutely maximally entangled states. So let's take the case of 4 particles, A, B, C, D. Okay, this is the most general state, is specified by these coefficients here, d to the power of 4 coefficients here. And now if you ask what is the entanglement of AB with CD, then that's given by the reduced density matrix, which you get from this matrix, which is this matrix U, which is simply Ij. So we just partition this into AB, that is Ij corresponds to A and B, KL corresponds to C and D, Ij KL. So if we write this matrix U, which is Ij KL, which is given by this entries here, Tij KL, if it is unitary, then this is maximally entangled. And now you can ask, what about AC? Is AC maximally entangled with BD? And you will see remarkably that this is exactly the question of the realignment. Is the realignment unitary? And if you ask, what about CB versus AD? Remarkably, it's just the partial transpose being unitary. So, and that's all that's there, by the way. BD is, if AC is maximally entangled with DB, then DB will be maximally entangled with AC. And therefore, if this matrix U, which I've identified from these coefficients here, is unitary, and all its both its realignment and partial transpose are unitary, then this state is a maximally entangled state of 4 parties. But in fact, we have just seen when we are looking at orthogonal Latin squares that permutation matrices, which are also unitary matrices, in fact, they are orthogonal matrices, so there are special cases of this, are exactly like these. So orthogonal AME, or absolutely maximally entangled state of 4 parties, exist in all dimensions wherever an orthogonal Latin square of dimension D does. So in fact, we can take this orthogonal Latin square, which I gave earlier, for a 3-level system and write a 4-party 3-level system's maximally entangled state. Okay. So every orthogonal Latin square leads to an absolutely maximally entangled state. So it's a very remarkable connection between combinatorics and quantum states and entanglement theory. Okay, now let's see, what about AME4-2? Because OLS2 does not exist. So actually that also does not exist. There is no absolutely maximally entangled states of 4 qubits. Without going into details about this picture, I want to say that we calculate some kind of entropy because we maximize entropy. So some entropy is being maximized by this absolutely maximally entangled state, and we normalize it so that the maximum entropy is 1. We see that for the case of qubits, it's not reaching 1. It's just going to 0.6, say it's in fact going to 2 by 3. Okay, so our goal is to, whereas for qubits, it goes all the way there to 1. Our goal is to do it for D is 6, because there does not exist an OLS of dimension 6. So we search for this. I don't have the time to go into the details of it. It's a combination of numerical and analytical methods. To give you an idea of the kind of numerical methods, we start with a permutation which is almost an orthogonal Latin square. You see, here this is actually such that there is no repetition along the first row or the along any row or column, but it's not a permutation because there's a repetition here. Okay, there's a repetition here. But this is a minimal. It's like you almost solved a sudoku, but you got something wrong. So we start with something like that because there does not exist a perfect orthogonal Latin square. And then we realign it. We take the corresponding permutation matrix. We realign it. It's not going to be permutation matrix or unitary. And then we take its partial transpose and we find the nearest unitary to it. Then we iterate it and so on. And it's a complex algorithm, but I mean, not complex. Actually, it's a simple algorithm. But what makes it complicated is the kind of seeds and the space, the dimensionality of the space. But quite remarkably, we found after a lot of spirited search, which I won't go into the details here, we found actually that it does go towards that there does exist unitaries of this kind, such that both partial transpose and realignment are unitary in dimension 6. And I just state here the solution which was found. The analytical methods involve using the fact that local unitary transformations don't change the nature of these realignment and partial transpose being unitary. And so it's actually a 36 by 36 dimensional matrix whose non-zero elements are written here: 1 1 6 3 2 2 6 1 1, etc. And actually there is very interesting block structure, okay, which is there. And it involves only 3 real numbers, a, b, and c, positive numbers in fact, such that c is 1 over root 2, and a and b, ratio of it is a golden mean, and its squares add up to half. But it's complex. We haven't found a real state. And the complex number which is coming in here is a root of 20, is a root of, 20th root of unity. So it has these simple numbers. It's got a golden mean. We call this the golden Arme state. There are many things which we don't understand yet, but we do understand several things. So what does it mean? And why should we say that this has got anything to do with a Latin square like what we discussed at the beginning? So let me say the following. Here is the state psi AB. So why? So you see, I said that any a pair of indices determines the other two pair of indices. How it appears in the quantum domain is that if you take any two particles, we can write this Arme state in the following way. We take ij corresponding to AB, then this is an orthogonal set of states for CD. And we can do it precisely for every other particle exactly the same way. We can take AC and write another orthogonal set, AD and another orthogonal set. The fact that they are orthogonal means that we can differentiate them exactly. And therefore, if you know the state of any two of them, you can determine exactly the state of the other two. So they are entangled in such a way. So that's why we are using this picture of a dice in our work, because it has 6 possible states, like our 6 here. And if you toss this in an Arme state, and if you measure any two of them, due to this entanglement, you know the other two, although these two can appear in completely random ways. But they are entangled crucially. They cannot be unentangled. And therefore, this is an entangled solution. Going back to Euler and his officers, although I'm not writing it in terms of regiments and ranks, anyway, there's plenty of war going on even now. Writing it in terms of cards and their ranks, you see that these cards are now, they have to be entangled. Okay, this means that ace and clover is entangled with king and spade. There's a superposition of these two with equal weights. These weights are given by the symbol of this thing here. But there are many interesting designs if you look at this closely. This is what the quantum solution implies. I won't be able to go into the details, but please, you can, those of you who are interested can look at the paper. So to summarize, Euler's classical problem of 36 officers is impossible to solve. We have not solved an impossible problem. There are no permutation matrices such that its realignment and partial transpose are also permutations. However, when we go to quantum mechanics, permutation matrices are special cases of unitary matrices. There are unitary matrices of size 36 that do have this property, but we have found that they have to be complex. It's not orthogonal. So we conjecture that that's not possible. This leads to a state of 4 particles where the choice of any two of them renders the other in an orthogonal set of 36 entangled states. The crucial point is any two of them. There are many uses I have not gone into: quantum error correction, parallel teleportation. I mentioned teleportation for ordinary entangled, maximally entangled states. In fact, these objects have been called variously two unitaries in some contexts. They've also been called perfect tensors by those who are studying quantum gravity, ADS-CFT correspondence. And it's been used a lot in many body physics of late. That's another very interesting work which I'm also pursuing with my students and postdocs and other collaborators. Many open problems. In fact, how many are there? How many such are there equivalent? And what about more than 4 parties? So I'm happy to say that we were able to solve this problem after a very long time, in fact. But it does open up a very interesting field of quantum combinatorics, which is already underway, and we have made a small contribution in that. So I thank you for your attention, and I'm sorry for the hitches in getting this thing to work. Thank you.
Thanks, sir, for such an interesting and nice talk, kind of very real introduction in a really complex topic. So let me thank you once again before I move to all the audiences. I mean, if you can ask questions if you have any. I have to unmute, right?
Well, I guess you're not seeing my slides anymore, right?
Right. Okay. So nothing from the participants, so maybe I can take this opportunity to ask my doubts. So actually, there's kind of a naive question in the sense that there are this army states, and that you have kind of found or defined rather in that way that realignment as well as the partial transpose. I mean, both of them are themselves, and that is how you define it.
They're
But
not themselves, they're also unitary. They need not be themselves.
Okay, they are unitary. Okay.
They are
But
unitary. They are in general some other unitaries. In fact, if they are army states or they are 2 unitaries, they cannot be themselves.
Okay.
So they form distinct unitaries.
Okay. But there will be a lot of matrices which will be missing in like one of the criteria than the other. So
Yes.
is there kind of a hierarchy of entanglement through which one can like approach this problem?
Yeah, it's a good question. Like for instance, we can have partial things. So let me see. Yes. So let's look at this picture, for example. Okay. Suppose that only AB is entangled, maximally entangled in this with CD. There are 3 possible partitions, but AB is maximally entangled with CD, then it simply means there's a unitary matrix. Okay. So there's already some amount of that's there. But this one is the next degree of this thing when both AB is maximally entangled with CD, but also AC is maximally entangled with DB, in which case this realignment is unitary. So of late, it has been discussed in as dual unitary operators. So there is a trend in many body physics where they found that actually there is some space-time duality which is originating from this operation, and they are calling it dual unitary. But in the math literature, apparently this has been studied as biunitaries for some time. Okay, so that is another level. So if suppose you were to study only unitary operators which are dual unitary, then that forms a larger class of which the 2 unitaries are a special class. And similarly, you can then go from unitaries to states. So the states will have partial this thing. So instead of absolutely maximally entangled, you can have what's called 1 uniform, 2 uniform, and so on. That's another way of doing it. This one is still a different way of doing it. But if the partial transpose is also unitary, then it becomes 2 unitary or this kind of absolutely maximally entangled state. But definitely there's a hierarchy.
Okay. Okay. And in the almost last slide, you mentioned about this relation with orthogonal Latin squares, where you are saying that the two parts are becoming orthogonal. So
Yes.
where you have written the state. So is it something to do with like, I mean, is it connected with MUBs in some sense?
It's also a
Because
good
you have now
question.
found.
We wish that it was connected to MUBs because MUBs, as you know, there is another source of rich open problems in MUBs. For those of you who are not familiar, mutually unbiased basis is collections of bases so that every vector inner product with another basis vector from another basis is equal. So the existence of MUBs in 6 dimensions is unknown. The number of them. There's only 3, I think, is known. Whether there exists more, for example, 7 is a maximum number, is unknown. So, Shashi, there is some connection with MUBs, but it's not perfect. But I think it's something which has to be explored more.
Okay. Thanks. So,
like for instance, I don't know whether these psi ij prime, these are MUBs in this. Maybe this is known. I'm not sure at this point. Yeah.
Okay. So since I can't see any raised hand or anything, so let me thank you once again for accepting our invitation and giving a wonderful talk on such a nice topic. And thank you. Thanks a lot.
Thank you very much. Thanks a lot to you, Shaji, and Professor Shom, and all others from VECC. Thank you.